All right, gang, Math 6620, Logistic Regression. I got to tell you, I feel like a total geek when I teach Logistic Regression because I like this stuff so much. And it's kind of embarrassing to admit that, but there you go. I just did, and you got it on tape. Guys, again, this is just something I really like teaching, and I'm I find myself like in dissertation for students I have that are working on their PhDs or DNRs or whatever it may be. I'm always trying to get them to do logistic regression, and they always don't like it as much as I do. So, okay. Anyway, don't know why I'm on this little tangent, but I am, and you guys are probably thinking, Doug, stop talking, get to the good stuff because we're busy. All right, so let's do that. Guys, we talked introduction to logistic regression previously, and something I want you to know from here. Let me give you just an indication of what we're going to do in the next two videos. We're going to set up a problem. Data set's been uploaded to Blackboard. I think it's called Success or Tutor or My Math Lab or something, and it's a data set that we're going to look at. The effects of Friday tutor sessions and number of hours spent on my math lab to predict course success in a 1010 course, Math 1010. Actually, it's Math 0101 now, but it's changed. So anyway, guys, logistic regression, again, is about taking a set of predictors and trying to predict the probability of group membership. More specifically, logistic regression, the output, the y, our dependent variable will be dichotomous. Dichotomous means zeros and ones. So this or that, true or false, succeed, not succeed, live, die, anything that can be dichotomously coded, and you want to set up a model to predict that, logistic regression is the tool for you. Now, I'll tell you one thing I did too. Yeah, I know if you've been paying attention in the videos, the fact that our screen here has been collapsing has just been annoying the crap out of me. So I downloaded a new, some new software for this Ziggy HD that I use. So hopefully that the problem's taken care of. And if it's not taken care of, we're going to find out real quickly, and you're going to hear me complain once again. So guys, anyway, logistic regression. Just to give you an indication, there are different methods that are out there. Just again, like there are for simple linear regression. One method that we'll explore is called forced entry, and another is stepwise. And in terms of stepwise, we can have a forward or a backward stepwise elimination process. This is the one that I prefer the most, the forced entry, because this is where we get into if we want to test a theory. If we want to get into kind of an exploratory analysis, and we're okay with the computer doing, you'll never guess what my dog wants to do. She wants to go out. This is unbelievable, her timing. But if we want to do exploratory, we could use a forward, backward, stepwise logistic regression. So let me explain these to you a little bit. At the end of the day, forced entry just means we've just put all of our predictors in, and we examine the coefficients and we examine the overall model. Stepwise works a little bit different. Stepwise, the backward elimination is going to throw all the variables in, and then it will take the first it will take the coefficient with the highest p-value that's not statistically significant. It will take it out, re-examine the model using a comparison of something we're going to learn called deviant statistic, and see whether or not the model experienced a significant improvement. Forward elimination, on the other hand, starts out with, now I forget, these work differently, but I'm pretty sure it calculates the p-values for all the coefficients, and it throws the the variable n that would have the lowest p-value, and then it adds variables from there on out, and to see when we finally add a variable that doesn't create a statistically significant difference. Now, by the end of this video and the next one, you're going to be pretty darn good at creating dialogue about what all that means. So guys, again, we're going to focus on the forced entry component, and that's just where we enter all the predictors and examine not only the overall model, but examine each predictor. So guys, to keep things kind of in tune, I like to keep these things closely, like a new technique, closely aligned with what we did in 5500. But this is, obviously going to be a little bit more advanced. Okay? So guys, again, are we testing a theory, or are we doing exploratory analysis? I'll just go ahead and tell you, I don't like this. I don't like exploratory analysis. I don't like for a computer to think for me. I like to create my theory. I like to test it. I like to publish it and go on with my life. Now, in moving forward, throughout teaching this technique, I've tried to bounce new ideas in logistic regression off of old ones back from 5500 in multiple regression. Clearly, there's obvious differences, and one of those is linearity. You think about linearity. Which, by the way, is an assumption. For logistic regression. But for obvious reasons, it doesn't apply here. It's clearly violated because y takes on values of 0 and 1. So guys, in terms of linearity, what's our solution? And you should know this by now. Our solution is use the log of the data. By using the log of the data, we turn something that is categorical and clearly not linear into a linear association. So the linearity assumption at the end of the day in logistic regression is there is a linear association between any continuous predictor and the log of the dependent variable. So I think this is important enough to put, I was just going to say that, I don't even think I can repeat it, but let me see if I can. So the linearity assumption in logistic regression is there is a linear association between all continuous predictors and the log of our dependent variable. Actually, I think that's pretty close to what I did say, so I don't think it's word for word, but I think it's close enough that makes a little bit of sense. Okay, so guys, for logistic regression, our assumption number one is linearity. It's clearly violated. What do we do to keep it from being violated? Well, we apply the log transformation, just as we let me get this thing centered here. Okay, just as we did back in log linear analysis. You should always know in statistics that one of your assumptions is going to be independence, and this is the only time, obviously you're not going to have that, is when you get into repeated measures. situation, but those procedures accommodate for lack of independence. And as you might imagine, this is still the most severe threat to logistic regression. At the end of the day, independence just says we can't take multiple measures on the same person. A new threat to logistic regression, actually something I want to get into just a little bit here, is something called multicollinearity. Guys, at the end of the day, and we're redesigning 6500 right now, so I'm not really sure how this will play out in 6500. In fact, we're redesigning 5500 and 6500, so there's a chance that multicollinearity, which used to be taught in 6500, is going to be thrown into 5500 to accommodate, to allow for some other things to be covered, which I think is a move in the right direction. So just because you guys are kind of caught in potentially the transition, I want to go into multicollinearity maybe more than I did would have otherwise. Okay, so that's the reason for this. Something that might appear to be, one of Darbro's many tangents. All right, guys. In a nutshell, if predictors are highly correlated, I got something in my eye, hold on. Okay. If predictors are highly correlated, then multicollinearity issues are present. And multicollinearity issues do all sorts of crazy things with the error sum squares. But I think one way to examine multicollinearity is look at the most extreme case. So imagine that we had x1 and x2 that we wanted to use to predict a continuous dependent variable. So we would be using a multiple regression technique, not logistic regression. Okay. So what I want to assume is that the relationship between x1 and x2 is a perfect, it's perfectly correlated. And what I mean by this is that our R value here is either plus or minus 1. And what will happen in this situation is we will get no random error. And typically, when people say you're not going to get any error, you think, well, that's a good thing. Well, actually, it turns out it's not a good thing because of the statistical dilemmas that it creates. So what we'll end up with, if we have a perfect correlation between, for example, x1 and x2, we end up with a multiple regression model. Actually, we end up with multiple regression models, multiple models that lead to the same perfectly fitted values. So we create, again, a statistical dilemma, statistical nightmare, because we get a good fit to our data, but we get many different models with the same fit. So the way I like to think about that is we get into a situation where we don't have uniqueness, which we would expect in a line of best fit, right? Now, if you, I pulled out this model, this data, just to illustrate this. So if we have 4 observations, and let's say that we have 2, 8, 6, 10 as our the data we've collected from one population, and then 6, 9, 8, 10. I tell you what, my dog is unbelievable all the time. It's the first time the dog's barked in 6 months. Well, actually not. All right, guys, hold on. Let me let the dog out. Sorry, come on. Come out. All right, sorry about that. FedEx guy came and dogs went crazy. So guys, the Y values are 23, 83, 63, and 103. Now, if you look at that, it looks like a very harmless data set. It looks like we could easily predict Y from X1 and X2. But it turns out, and I'm not going to show this, but it turns out there are two fitted regression equations that would nicely fit this model. For example, negative 87 plus X1 plus 18X2 fits it perfectly. And another, and trust me, there's more, is minus 7 plus 9X1 plus 2X2, which also fits the model perfectly. Yet, when we look at these models, they have comparatively different magnitudes for X1 and X2. In this situation, X1, the magnitude of X1 for this model is larger than this one, but for X2, the magnitude for X2 in this model is larger than the other one. Well, that seems kind of wacky that we could say that comparing the magnitude of X1 and X2 varies according to two models that perfectly fits our data. So, guys, that essentially is what multicollinearity does. And the problem today is our statistical software packages are so powerful. If you get multicollinearity issues, these statistical software packages are so powerful that it will, kind of go just pound through the calculation dilemma with the matrices, and it'll give you, it'll give you coefficients, and it'll make you think that that you got a viable model when actually you didn't. So. So guys, three assumptions: linearity, multicollinearity, and of course independence. Now, guys, a lot of other stuff can go wrong too with logistic regression. First of all, unlike simple linear regression, the MLE does not result in a closed form solution. And what we do is we actually get into a quadratic and solution, and technology, in our case R, will actually perform an iterative process, which I'll show you the results of when we get into R. So again, this iterative process is implemented with the hope of converging to a solution. Now, sometimes it doesn't converge, and sometimes the R, in our case, the computer would just give up, and other times it'll give you an answer when it shouldn't have given you an answer. So, guys, keep in mind, just because we get an output doesn't indicate it's a reliable model. And I'm going to show you throughout this video things that we can take a look at to look at that. And at the end of the day, you look at the standard errors. If the standard errors are really huge, then it indicates that you've probably got some of these issues with the calculation of the betas for logistic regression. So, again, if you suspect this, a lot of people just do nothing and try to publish it. Don't do that. You're not going to get away with it in your master's thesis. Check cross tabulations for all categorical predictors, something that you might consider, and look at your standard errors. So I would prefer between do nothing, looking at multi-way cross tabulations between categorical predictors and standard errors. Clearly, I don't prefer number one. Number two would be probably most preferred. And number 3, examining the standard errors. That's so easy. It's kind of like, well, why wouldn't you do that? So, well, boys and girls, we are almost getting to some fun stuff. Now, one more thing I want you to have on your radar is the separation issue. All right, so let's talk a little bit about separation and something that may happen. Separation and lack of separation both create lots of problems. So lack of separation would look something like this. Let's say that we have a continuous predictor x, and we have our y, which is going to take on some value of either 0, 1, and that it either happened or it didn't. Well, if we end up getting data that looks like this, notice the huge overlap. Now, guys, a little bit of overlap's okay, but notice the huge overlap there. And that would be lack of separation. And if we get a graph that looks like this, then let me draw a red flag here. Pretend that's red. That would be a red flag. Another situation that would create an issue for us to keep in mind, and again, I'm speaking in terms of having continuous predictors here, is something like this. Something like this, notice we've got tons of separation between our outputs. In other words, we have a pretty significant interval on X where we have no data. And the problem here is the software doesn't know what to do for the interval that happens between where we have data and where we don't have data. So in other words, when it fits this, is it going to come out here and do this? Is it going to come out here and do this? Well, it doesn't know. And again, insert red flag. So, guys, when we look at our graphs, this is, we're not reinventing the wheel here. It goes back to the reason we examine things when we're going to implement a statistical technique. If I look at a relationship between x and y and I'm running a simple linear regression and I get something like that, well, 2 thumbs up, let's do our stuff, right? But what happens if I have more data and I examine the initial scatter plot and it looks like this? Well, that's not the tool to use. And that's all I'm saying up here. We examine things graphically to point out the obvious red flags in implementing a statistical procedure. All right? All right, gang, let's have some fun. Let's get into R to examine a logistic regression problem. And guys, what I've done here is I've uploaded a data set, and again, I think it's called Tutor, but I'm not really for sure. But my y value is either succeed or not succeed. And we're going to predict this from a categorical predictor and a continuous predictor. And what I did, one of them, it's called Tutor. And Tutor is, did the student attend Friday tutoring sessions? Easy for you to say. So, and I forget how this was actually broken down. I forget exactly. 0, no, 1, yes. And it seemed like maybe they had to attend, 5 or more that they did regularly attend. Or again, I forget exactly. Another thing we're going to use is we have a My Math Lab. And this is just the number of hours. Actually, that's not right. It's a number of days the student spent 1 hour or more on my math lab. My math lab's got a really cool learning module for students, and some of our Math 1010 professors are trying to implement that to make some cool things happen. In other words, get students to succeed in courses that have unusually high, or I should say unusually low success rates. All right, guys, a couple of packages we're going to need. We're going to install what's called CAR. You've probably already installed that, so if you have, all you'd have to do is just access the library. And then we've got something else we're going to use called mlogit. So guys, again, what do we need to do? We need to do install packages. You guys remembering those? That's got to be in quotations. And then we've got to access the library for the same things. We'll have to do that for both of these, okay? Well, guys, I think we got everything set up. I think we're ready to do some stuff. By the way, it looks like my my download actually did some cool stuff, right? I haven't seen that I'm too anal retentive to be teaching a class online. All right, gang, let's go for it. I've got R. I've already got it up and running. Let me get this down. Okay, so what I've done here is set my working directory. I did it incorrectly at first, and I've just got my data frame called data in it's actually called tutor. I thought it was called something else. All right, guys, hold on. Gotta get the dog. All right, Darber uploaded a 60-minute video, and 52 minutes of it was spent working with his dog. All right, gang, let's see how this happens. As we saw in log linear analysis, especially when we were computing the odds ratios, and it turns out odds ratios are going to play an important role in logistic regression as well. The reason I wanted to teach these two things back to back. Order is extremely important. When we were calculating odds ratios, did we go from success to non-success or non-success to success? In which case, you would get completely different. Different odds ratios. So, guys, we got to take care of that. And it turns out that because this is such an important issue, R created a very easy way to ensure that you have your baseline group set as you want it. So what I would like to do here is I would like to let no be lack of, and that's typically the way I like to do it. Lack of success, lack of life, lack of whatever. So lack of attending Friday tutor sessions. So ultimately what I want to do here is for success, I want my baseline to be no. And for tutor sessions, I want my baseline also to be no. So guys, what we'll do is we'll just create a new factor. And so what I'm going to do here is I'm going to go $success. And I'm just going to do what's called re-level. Data success. No. So guys, that simple entry will set no as my baseline for success. And again, success was C or higher, they succeeded. C minus or lower, they did not succeed. And the reason you want to do this is because the interpretations of the coefficients and ultimately the coefficients raised to the e raised to the coefficient power becomes extremely important in understanding our model, and the interpretation of this deals with 1 unit increase in our predictor variable. So it's better if we can set things going from 0 to 1 instead of maybe 1 to 0. Guys, going to do the same thing here. I'm going to cheat a little bit. I really don't think it's cheat. But the other variable that you'll have here is called tutor. Did they attend the Friday tutors sessions regularly? So we'll get that. All right, well, that's fun. I don't understand that. Let me see. Maybe I forgot one of my data. Okay, I see what's happening. Actually, for tutor, I don't have this as no. I've got it as none. So let me take care of that. Okay, so tutor, if they didn't regularly go to Friday tutor sessions, I don't know why that was put in as none, because it makes more sense to put that in as no. All right, gang. To run a model, it's really, really easy. But again, let's not get too crazy before we take care of our install our packages. So guys, I'm going to take the chance that I've already installed the package for car. Looks like I have. If it doesn't find car, it'll tell you that, which means you'll have to go back in and do install.packages. And again, car would have to be in parentheses. I want to see if I've done this one. I'm pretty sure as much. Yeah, okay, cool. I was going to say as much logistic regression as I do, I would think it would be, but of course I could have done it on my other computer. So, guys, to run our model, man, it's just simple as can be. We just run a GLM. Now, let me explain to you what I want to do here, because I've worked this out a little bit, and I know what's going to happen. So I want to look at this essentially in terms of 3 models. I want to look at just an intercept-only model. Then I want to look at predicting success from tutor, and then I want to create a third model which looks at creating success from tutor and the hours, what number of days the students spend more than 1 hour in my math lab. So guys, the very first thing I want to do is I just want to look at success as it's predicted from tutor, and the family distribution that okay, guys, I can type, I just can't see, is binomial. So when we want to run a logistic regression model for maybe obvious reasons, we are interested in the binomial distribution. Guys, come up with a summary of the model, and we get stuff. And I guess this is actually where the fun begins. Now, when I look at something like this, we're trying to make heads or tails out of just what the heck's going on here. And, well, the first thing that I like to look at, I don't know why I'm just kind of obsessed with this, but I like to look at the number of iterations that it took for to get convergence. And it took 4, and it seems like in many situations 4 is kind of the magic number. Deviance, residuals, we can see that these things are relatively symmetric. We get into an examination of the coefficients, and down here we get into an examination of our model. So again, just like multiple regression, where we got into the F statistic, p-value, R squared, that examined the overall contribution of the model, or the overall assessment of the model. We do that in logistic regression as well, but we also want to come in and be able to examine our coefficients independently. So guys, again, I first of all look at the number of iterations, which was number 4, and I think the next thing I'd want to do, you know what, I'm going to try something. I don't know if I'm going to be able to pull this off or not. I would like to be able to Watch me, I'll get real fancy here and my computer will crash. I'd like to be able to write stuff as I'm going along. So let's see if we can go split screen on you here. Okay, so let's first of all, I want to look at just the overall fit of the model. So I'm going to examine the model fit first. I'll get into the coefficients here in just a second, but right now I want to just look at the overall fit of the model. And I am going to be automatically, just my eyes are going to come down here to the null deviance and the residual deviance. Let me tell you what the difference is. The null deviance is that negative 2LL measurement calculation, but this is based on the intercept-only model. Working much in the same spirit as log linear analysis, we kind of examined the worth of the model essentially in how much did it change when we added a predictor. So the residual deviance is actually after we add the predictor tutor, and we can see that the deviance, the negative 2LL, decreased approximately 10 units. And we can see that we have the degrees of freedom. Now our question is that change statistically significant? Now a couple things about the deviance. Remember, this is calculated as negative 2 times the log likelihood. Something else to recall, that higher value or a larger value indicates a poor fit. Okay? So we ultimately need to get in to where we can actually compare these. So I want to be able to compare our null deviance, and I like to think about this as the baseline, with our residual deviance, which is our new model. Guys, our new model is we just have the predictor that we've added. So guys, our baseline deviance is 154.08, and our residual deviance is 144.16. Now, what we want to do is we want to compare these, but as you know, that comparing two things statistically has to do with the standard error. Are 10 and 12 close? Well, if the standard, let's just keep it in terms of standard deviation. 10 and 12 are really close if the standard deviation is 15. But 10 and 12 are not close if the standard deviation is 0.1. So again, closeness is relative based on the unit of spread, or the measurement of spread that we have, and in this case it's going to be the standard error. So guys, the question is, how much better is the model, if at all, and is the decrease statistically significant? Now, what we want to do here is we want to create, and I want to go back to where we get R, where we can see it. Okay. What I want to do is I want to calculate the chi-square statistic for the difference in the null deviance and the residual deviance. And what I do here is I'm going to create what's called a model chi-square 1, because we're going to run two models ultimately. And I want to do, so model, and what did I call that? Just model? Yeah. So model for the null deviance minus the model $sign for the residual deviance. Okay. Now, if I want to see that, you know, that's cool. Okay. What? Let's see what happened there. I don't know. That's never fun. Maybe it just. Okay, there we go. That's what I need. So, guys, even though it is the residual deviance, we don't put residual there. So you know, don't do that. So it's just the deviance of the model. So now, guys, we get ultimately this 9.926 is our test statistic. But as we know, test statistics are relative to the underlying sampling distribution that models this, and it turns out, again, it's the chi-square. But what we got to do now is we clearly need to come up with our degrees of freedom. So I'm going to call this the model chi1 df, and I'm going to go model $df dot null minus model $df dot residual. And what this should do is subtract our degrees of freedom, which you might say, well, Darby, why didn't you just subtract 111 or 112 minus 111? Because I'm not necessarily working this problem for this problem, working this problem for future stuff. All right, gang. So what's really going on? What's the rest of the story here? I guess as Paul Harvey would say. Do you guys even know who Paul Harvey is? Are you too young? All right, gang. So what we got going on here is pretty simple. We've got a chi-square distribution. So chi-squared degrees of freedom 1. We have a test statistic of 9.926. Our p-value is the area to the right of that. We can use calculus or we can use R. So we're going to use R to make that calculation. So guys, remember we've got in previously to this PT, P norm, P chi-square that we can use to calculate area under the curve. But what we'll want to do here is do 1 minus P chi-square of, let's see, 9.926 should get us pretty close, comma 1. So guys, we end up getting a p-value of 0.0016, which clearly is less than 0.05. Actually, it's statistically significant at the 0.01 level, not at the 0.001 level, but it's close. So guys, what we have here is that the second model, the model that includes success, is an improvement from the intercept only model. That's because of the statistical significance. I think I'll break this down. I'm not really sure what I'm going to do in the next video, but I think in the next video I'm going to break this down to where I actually set up more clear and concise statistical hypothesis for this. But so gang, I don't know what I'm looking like on time. It looks like I'm getting close to my hour. So I'll tell you what, I'm going to end this, and the next video we'll take off right where we ended here. So guys, take care.